There's another aspect of gravity, which another fellow brings up, and a lot of people bring this up and they have it in the back of their minds anyways. Those who do bring it up and those who don't, they all have it in the back of their minds, and it's a valid issue. And here it is. Okay, let's put this there. And the fellow says, Gide has conveniently given the specific object and no other in the universe the property of intangibility. So we have an object that can't be touched. Okay, correct. The assumption is irrational. Okay, I don't know, he didn't specify why it's irrational. Okay, and that's unfortunate. It'd be nice if he could tell us what he means by irrational and why this assumption is irrational. We say the opposite. We say it's quite rational because we define an object as that which has shape. And there's no provision for see or touch in the definition that we just made. Object is that which has shape. See and touch play no role. No senses play any role whatsoever in the definition of objects. So why is it irrational? I have no idea. He hasn't explained that. And yes, we do define irrational as a theory that does not include objects and has lousy or no definition whatsoever, or definitions which are used inconsistently throughout the dissertation. Okay? And then he says, how can you have a rational theory with an irrational assumption? Well, it's not an irrational assumption. He has not explained why he thinks it's an irrational assumption. Okay? That's the whole issue. Okay, so here we have, just to rub it in, that he's correct when we say that the rope cuts across. So you have a rope, okay? And I know this is hard for a lot of people to imagine, right? We have a rope, right? And I'm saying if you have two ropes, like for example, like that, right? This rope can go right through the other rope, okay? It cuts across. That's what we're saying, okay? Let's make sure we understand that we're not trying to elude the question. We're trying to confront the bull by the horns, right? We're going to grab by the horns. And what we're saying is this goes right through it. Okay, I hope that's understood. Let me show it here. We're saying that if a rope comes through, they will go right through it. Okay? That's understood, hopefully. It's not that, people, are you crazy? Bill, are you crazy? No, that's what we're saying. Okay, so let's explain one way that happens. Okay, so that's one of the things people want answered, and we will answer it. Here it is. We're showing an atom approaching another atom along a rope that connects them. Okay, now this is a specific situation. Okay, there are other situations. Right now, we're just going to address this one, and we're saying that if an atom approaches another one along the rope that interconnects these two atoms, the atom does not push on the rope. It's not being pulled by the other atom either. What it does, it slides along, and since the rope forms the electron shell and also the proton dandelion, the proton star that's in the center of that, then what it does, the rope simply goes around and momentarily forms that atom and then continues behind it. That's what it is. So what's happening is the atom is sliding like a bead on an abacus without affecting the wire. Okay, that's more or less what we're saying here. As the atom pumps back and forth and does its quantum jump, right? It's expanding and contracting, and as it moves forward, it eats into the rope, and one thread goes around, the other one goes through the center, and it doesn't affect the atom at all. And what you're seeing here explains why the speed of light is not added to the speed of an object. Like the train, the train going along the tracks and you turn your flashlight on. We don't add the speed of the train to the speed of light coming out of your flashlight. Why? Because the flashlight, every atom in the flashlight, every atom in the train is moving through the ropes that interconnect every atom of the train and the flashlight to whatever's in front of it. So it doesn't push on the rope. It can't beat the speed of the torsion in front of it on the rope either. So that's why you do not add the speed of the object that's moving, the source, right, to the speed of light. Okay, hopefully that's understood. That's what we're trying to explain there. Okay, and here let me show you another version of this, another vision, so that you can hold this in your mind as well, ponder it. Okay. And here we have a hand, and the hand's going to go to a ball, right? Hand's going to move and try to grab the ball, okay? So we're going to show here 5 atoms, 1 atom for each of the fingers. Obviously, you have gazillions of atoms in each of your fingers. We're just going to look at 1 in each finger. So your hand moves forward trying to touch the ball. Why doesn't it push the rope? Well, because the atoms in your hand are sliding along the rope. And the rope essentially is forking out at the electron shell of each one of those atoms. And one's going around forming the electron shell, and the other one is going through forming the proton star. That's the theory, okay? Now, that's only when we move like in a straight line, okay? So this is a specific situation, moving along the rope that can interconnects any 2 atoms. That's one situation. The other one is if you have your hand and you got an atom in each of your hand, right? And what it's doing as you move straight, let's assume you move perfectly straight, again, you're sliding along the ropes, the invisible, intangible ropes. Can I cut across the ropes? Like I just showed here, right? Hopefully we can. Hopefully we can. And that's what we have to explain, okay? Because that's the way Mother Nature works. First, we have to make sure that we all understand that there had better be physical mediators. Mother Nature doesn't do black magic. She works with mediators, not with abstract concepts invented by man, such as energy and field, okay, or wave or time. Mother Nature works with physical objects that we cannot see or touch. Now, how do they cut across? Well, it's not a how question. It's what is it that we don't understand as human beings? What's different between what Mother Nature does and what we are understanding? That's where the problem is, right? And so I'm going to state it here that every theory ever devised by man, anything invented, developed, any explanation, any theory, any physical interpretation, any mechanism that anyone ever concocted for how the universe works, all of them, even the one you have right now, has objects going through objects, things going through things. People say, no, my theory doesn't do that. Yes, every theory has it, okay? And that's what I'm going to show today. I want to show that all theories ever devised by man, all theories ever concocted, even the ones we have today, even the one you have, all of them have objects going through objects. And if you deny it, all you're showing is what I'm going to say next, which is that the reason you never pondered it is that you use objects and concepts back and forth intermittently. You know, an object becomes a concept, concept becomes an object whenever you need the object, whenever you need the concept. So people use, for example, waves just as an example. So a wave is a concept. But people say, look, there it is. It's in front of you. That's a wave. They show you a wave, an electromagnetic wave, a transverse wave, right? Bunch of vectors there, and they show it moving, and people think, well, I'm looking at an object. I'm looking at something that's in front of me. It looks like some kind of shape that's moving. Okay, no trouble with it. But then when they do their explanation, they bring in the concept of the wave. And so people don't ask the question, how does a wave go through a wave? Because everybody says, well, yeah, it's an abstraction. Well, it wasn't an abstraction when you showed the movie. Now you're calling it an abstraction. And of course, when you treat objects as concepts and vice versa, what happens is you never ask the question, how do waves go through waves? Why don't waves crash against waves? Okay? Why don't particles crash against particles? So let's go through that. Let's go one by one. And so this is what we're going to show today. Here it is. This is what people usually illustrate. They have a heart and a brain. And, you know, it turns out the heart can't go through the brain or brain through the heart. Okay, so, you know, we have a problem there because when you talk about physics, you have to put a heart and you put a brain. So what do these people do? Well, they say, well, no, Bill, you got it wrong. See, we're not really talking about heart and brain. What we're talking about is love and intelligence. And there, nobody questions whether love can go through intelligence. Okay? So what they're doing is representing love and intelligence with a heart and with a brain. They're illustrating a heart and a brain, right? And then they do their physical interpretation with love and intelligence or love and mind or whatever. So this is where the problem is. This duality allows them to get away with murder. And more importantly, it masks the real problem, which is that nobody asks the question, how does love go through mind? How does love go through intelligence? Nobody asks that question. It never pops up because everybody said, well, it's an abstraction, obviously, you know. And so this is the problem. If you talk about heart and brain, we have a problem because they can't go through each other. Those are physical objects. But if you say, well, no, the heart really represents love and the brain represents mind, well, how does mind go through love? Well, that's not an issue. Nobody asks the question. It never pops into the conversation. It only pops into a conversation when you say, no, I'm talking about a rope, a physical entity. Oh, how does an entity go through another entity? Now the problem comes in. That's where the problem is, okay? So here we have quantum mechanics. What do they do? How do they explain all these things? Well, they have this thing called superposition, that an atom can be at two places at once, right? And it also has these two superimposed atoms. And what happens is they have two different states, as they call it. One is vibrating, the other one is not, or vibrating at a different rate. So we have essentially two atoms at the same place, and they have two different properties. One is vibrating faster or whatever, you know, to a larger extent than another one. And essentially what they have is superposition of two, it's not states, they have superposition of two atoms. That's what they're illustrating. They're saying there's two things there, and one of the things is not vibrating, the other one is. That's what they're telling you. But, you know, nobody questions that because, okay, it's a superposition of states. They use that, you know, roundabout language, and so nobody picks up on that. So we have to go to the system, you know, find out what they really mean, and here you have it. Let me get this one out of here. You have the bot, and we ask them, you know, again, can two particles occupy the same space, the same location in the universe? Okay, and there it is. There's the answer. Two bosons. Okay, bosons. There's several types of bosons, and there you have a list: mesons, gluons, Higgs, and photons, etc. Right? All those are known as bosons, and according to the bot, which is programmed by the mathematicians, right? Two bosons can occupy the same location in space. Okay, straightforward. Whether two atoms can occupy the same space depends on the type of atom and the laws of quantum mechanics. So can particles in quantum mechanics occupy the same space, meaning that not only can they occupy the same space, but they can go through each other, because if there's an atom or a boson, right, and they're coming together, and at some point they can occupy the same space, they can also go right through each other. There's no reason not to, okay? And we have a problem with that because there's a contradiction. You have here a paper written by a fellow by the name of Burke, 1997, and this is what he had to say about photons, okay? And he says the following: the positrons are interpreted as arising from a two-step process. Remember, he says interpreted. That means this is their interpretation of the people who wrote this paper, right? Which were about 20 of them, in which the laser photons are backscattered to giga-electron volt energies by the electron beam, followed by a collision between the high-energy photon and several laser photons to produce what? An electron-positron pair. So there's a two-step process. First, they're going to create an electron-positron pair, right? And now they're going to do something with these. These results are the first laboratory evidence for what inelastic light by light, also known as light on light, scattering involving only real photons. What they're saying is a photon bounces off, crashes against, collides against another photon. They don't go through each other. But then he clarifies, these people, they clarify, a complete theory of reaction 3 does not exist at present, so we performed a simulation. Okay, they're going to do a computer simulation based on a two-step model in which the beam electron emits a virtual photon according to the Weizsäcker-Williams approximation, which means that an electron can carry many photons on its back. Virtual photons, by the way. And the virtual photons combines with the laser photons to yield electron-positron pairs. In other words, what they're saying is they're going to create the electron-positron pairs. They're going to create them with virtual photons, and then they're going to do this magical thing where they say that light, meaning a real photon, now is going to bounce against another photon. They won't go through each other. So we have a problem because, photon is a boson, and the worldly wisdom today is that two bosons can occupy the same space, meaning they can really go through each other. And these people are saying that they proved in the lab that photons bounce, real photons, right? Not the fake ones, right? Not the virtual ones. Hit surface to surface, they bounce in opposite directions. So which is it? I mean, do they go through each other? Do they occupy the same space? Do they bounce away? Which one is correct? And so here we have it, okay? The virtual particles that this fellow talked about, virtual photons, let's make sure we understand what happened. Remember, this is 1997, right? And when I looked it up at the time, this is in my book, by the way, when I looked this up at the time, I looked at the Wikipedia to see what a virtual photon was according to those days, right? And here you see that, which was around the year 2000, compared to today, which is 24 years later, right? Almost 25. And here are the differences. This is what the wiki said in those days, the peer-reviewed encyclopedia, right? In those days, they didn't peer-review it as much. I guess they peer-reviewed it much more afterwards. But originally it said, a virtual particle is a particle-like abstraction which facilitates understanding of calculations. The term is rather loose and vaguely defined. They appear in calculations, but never as indexes to the scattering matrix. In other words, they never appear as the observable inputs and outputs of the physical process being modeled. Their existence is questionable. However, the term is useful in informal, casual conversation or in rendering concepts into layman's terms. Well, they had to take all that out because this destroyed the notion that this was science, and so they said, no, this is what it is today. Virtual photons have come a long way since then. So now it's virtual photons are a fundamental concept in particle physics and quantum field theory that play a crucial role in describing the interaction between electrically charged particles. Virtual photons are referred to as virtual because they do not exist as free particles in the traditional sense, but instead serve as intermediate particles in the exchange of force between other particles. Okay, so it's this magical particle they call the virtual photons, these fake photons, right, which they need to make the transaction, meaning their equations, come out right. That's why they put them in by hand in their equation. They say, we don't see them, we can't measure them, they're too swift, they come in and out of existence so fast that we can't measure them. But it helps, it's useful. Why is it useful? Because it makes our equations come out right. And so they say they're responsible for the electromagnetic force that holds matter together, and virtual photons are thought of as fluctuations in the electromagnetic field. So virtual photons are fluctuations, they're verbs, they're not nouns, okay? And yeah, if you have verbs can go through each other. You don't have any problem with that. I mean, hopefully anybody who thinks that, running can go through flying or through swimming, I think should have no problem in understanding that. Sure, they go through each other because they're not nouns. That's the issue. Okay, so here we have the synthesis of that. What mathematicians are doing, they're covering all the bases. Okay, there it is. Okay, so here's the million-dollar question. Do particles, waves of light, etc., quantum, right, these photons, virtual photons, whatever photons, right, do they go through each other? Do they occupy the same space? Do they bounce off each other? You take two lasers. Do they go through each other? Do the photons start bouncing off like if you took two hoses with water coming out of them, right? You point two hoses with a lot of water coming out of them, you'll see the water splashing in every direction because water will hit water and they'll bounce, against each other. Is that what happens with photons? Can you take two lasers or two flashlights, right? You point them so that their beams cross, right? Well, the photons bounce away like they do with water, with two hoses. And so, no, the answer is all of the above. What they do is they cover all the bases. Okay, they cover all the bases, and of course, when you cover all the bases, hey, you've got it made, because do they bounce? Yeah, they bounce. Do they go through each other? They go through each other. Do they occupy the same space? Yeah, of course. It's all of the above. And so that's the problem. And nobody ever questions this, because again, when it comes to that, they say, well, we don't do physical interpretations anyways. What we do is equations. And so why did we ask these people if they don't do physical interpretations? That's what you got to ask yourself. Why are we asking the wrong people these questions? Maybe we got to look for a genuine physicist that can explain to us, right? Instead of these people who moonlight as physicists, but they're really just mathematical physicists, meaning they're mathematicians and nothing but. Okay, so here we have another fellow. His name is Arvin Ash. I've talked about him in the past, and he's just going to go into the fields, and here you can see what happens to all the fields. They all superimpose, okay? And so here it is. Listen to him, okay? Don't listen to me, listen to him.
All these fields extend out in all of space-time. In other words, the fields are always there and exist everywhere, including inside your body. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum.
Okay, so is that magic? Or is that science, what you just heard there? Was that science? Or was that a one of these explanations pulled out of the bottom of his nose hole? Okay, so all these fields, they superimpose. Do they go through each other? Is field a physical object? I mean, they're talking about the vibration of this field, right? It becomes a particle. That's what a particle is in quantum mechanics today under quantum field theory. It's a vibration of the field, becomes a particle, and now it becomes a nugget, right? A grain of sand, okay? Now we have all these grains of sand, and not only of that field, we have the grains of sand of each field, of the gravitational field, the muon field, the pion field, the electron field. We have all these fields, and they're all everywhere. And we have these fields, they extend all the way to the edge of the universe. And we're talking about the fields of every atom in the universe. We're talking about atoms which we can't even see. There are beyond, our observable universe, right? We have galaxies that we can't see, and those fields, their fields extend all the way to us. So we have all these gazillions of fields all in the same place. Don't they interfere with each other? Or are we saying that they go through each other? Okay, so that's the question. The question is, do they go through, or do they bounce against each other? Do they occupy the same space? This is a valid question. I mean, we're going to talk about physics, physical interpretations, and they're going to treat the field as a physical object. Well, do they clash? Do they bounce? Do they collide? Or do they go through each other? I think it's a valid question. Okay, here we have the general relativity version, more or less the same. You have a black hole, and it's made out of what? Out of two black holes. Okay, here's the two black holes, and they're rolling around each other, right? And they send all these waves outwards, and eventually, because of this great mass, these two great masses that become one, all these waves come all the way to you. And this is more or less how they show it, okay, how they illustrate it. They have these two objects, celestial objects. They could be black holes. It could be two stars. It could be a planet and a sun, a star, right? And what's happening? They show the waves coming outwards, okay? Well, yeah, I mean, if you limit it to these two objects and say that these are the only two objects in the universe, right? Then you can illustrate it like they're illustrating it there. But now imagine gazillions and gazillions and gazillions of these, okay? Of these pairs of two objects rolling around each other, whatever, all of them creating waves and sending them in every direction, north, south, east, west, up, down, side to side, the whole works radially. And when you have that, then the question is these waves, see, they only show the waves of the of space-time. Now, if you if you have the waves of every object in the universe, they're all interfering. They're all going through each other. You won't have this neat, pond, stone in the pond type of pattern. What you would have is totally ridiculous, irregular waves. The wave would not be first two-dimensional, it would be three-dimensional, but it would be in every single direction. Every little bit of that space-time, the event, which is a point in space-time, every one of those would be interfering with the one next to it and with the one farther down. You would not have this pattern that they illustrate all the time. Okay, so the question is, if that doesn't happen, then are they saying that the waves go through each other? They're not interfering with each other. There's no clash. There's no collision between the waves. What are we talking about? What kind of object is that goes through another one? Is it like a rope, that goes through another rope? Is that like it is? All of these have the same thing. And here you have more or less what I'm trying to say. Here you have the famous electromagnetic wave there, okay? And you can see that it's a bunch of vectors that are moving. Very scary stuff, because each one of those vectors is just magnitude and direction. That's all it is. They have magnitude and direction. Now it's moving sideways. Jesus, it's very scary stuff. And here's one wave, okay, just so you can see. Here's one wave, okay. Okay, out of one incident, one phenomenon, you have these waves coming out. Here's another wave, okay, looks more or less like that. Okay, no problem. I can live with that. We have a wave there, right? And it's a little different than the other one. This is from another event. Okay. Here's yet another wave. Okay. Looks more or less like that. Kind of weird, right? So we have all these waves, right? They all have these different patterns. Okay. And just in case, let's show another one here. Okay. Here we have another one. Okay, it goes like that. Okay, we have all these waves, and they're moving everywhere in the universe. They're from different events, right? From different phenomena. Okay, and so what happens when we put them all together? Let's see what it looks like. It looks more or less like this. There you go. Now that's what you would get. You would get a big mess. You would not have those nice little stone in the pond type of ripples. You would get something like this in every direction, coming in, going out, going north, south, east, west, up, down, side to side, forward and back. You would have a whole mess. God would not be able to keep track of anything in the universe if this were true. Okay? So they always show you one, and so the question that you must ask yourself is, do these waves go through each other? How come they don't interfere with each other? I mean, we're talking about the waves in space-time, right? And space-time is not a number line like I say. What do I know? No, it's this physical entity, right? That's what's waving, and those are the waves they measure. If they can measure it, it's a physical object. Obviously, if it's a wave of what? Well, it's a wave of the canvas or whatever space-time is. The wave of events, of points. Okay, so we have this sandbox, all the little grains of sand. That's the universe, the sandbox, and all these little grains of sand are moving, vibrating up and down. There's waves all over the place. But see, one grain of sand can move up or down. It cannot move in 10 different directions at the same time. And the next one, the one next to it, can also move in only one direction. It moves up, it moves forward, it moves down, but it cannot move in 10 different directions, a million different directions at the same time. So the only way we can avoid collision is if they go through each other. Grains of sand going through each other. That's general relativity. That's so far also quantum mechanics. How about the other people like the electric universe? Okay, another group of people, dissidents they call them. Well, this is what they believe in, more or less. Here it goes. Well, this is really from the plasma universe, the one I'm going to show, but it's essentially the electric universe and the plasma universe are the same thing. Very little really differences between them. Here's the plasma universe. Okay. Looks more or less like this.
The plasma universe holds that the universe is 99% plasma, and that this plasma forms a vast network of filaments. Galaxies form along these filaments due to the interactions of the filaments. Filaments give it the structure and carry material around. But if plasma pervaded the universe, it could then carry electric currents. Space was filled with a network of currents which transferred energy and momentum over large or very large distances. The electromagnetic force was now equally as important, and certainly more important for the shaping of the large-scale structures of the filaments. The important aspects of the plasma universe, therefore, are that plasma will form filaments, pinches, double layers, and that many of the phenomena we see can be explained with these concepts.
So, are we talking about concepts or are we talking about structures? So they start with structures. They said these structures called filaments. What are these structures made of? Electric currents. Okay, so far so good. We have these filaments, I guess wires, metal wires. I guess that's what those filaments are. And then they'll put a wire. They say, see those bright lines? That's electricity going through them. We call all that flow of electricity, we call those filaments because that's what they look like when you look at the entire universe. Okay, so they have physical objects. And then they say, oh, these are concepts. Well, are they concepts or are they objects? Are they structures or are they some kind of abstraction? What are they? And so, but this is the issue. The issue is you have all these electrons. What is electricity? A flow of electrons. That's what the plasma people in the electric universe say. That electricity, the flow of electrons, they call them charges, right? But they're referring to the electron. These electron beads. Using Niels Bohr, Rutherford's model, right? The planetary model, proton with a little bead going around it. They can't justify that one, but let's forget about that for a second. So we have all these electron beads, they're flowing. That's electricity. Goes from one star to another star, goes from one galaxy to another galaxy, from every star in this galaxy to every star in that galaxy. And none of them collide against the gazillions and gazillions and gazillions of electrons flowing through the universe. We have all this electricity flowing, all this plasma which fills the entire universe, right? It's all electricity, right? They form these filaments, physical filaments, and none of these filaments cross across each other, go across each other. Like the rope going through a rope. All these electron beads, I guess they're beads. Otherwise, they have to tell me what it is. But of course, it never came into their mind to even ask the question because we're talking about charges. And charge is 1.6 times 10 to the minus 19 coulombs. That's what a charge is. Proven by Robert Millian, right? He proved what a charge is. Charge is a number followed by a unit value. And so we're not talking about little beads when we say, when we just say, when we have the flow, yeah, they talk about beads. But when they cut across, they say, well, it's just electricity, which is an abstract concept, which is, a concept, which is what they said. They went from structure to concept. And here you have the filaments, okay? This is what the electric universe, which are the inheritors of the plasma universe, right? And that's what they show. They show all these filaments, and people say, okay, I understand that. We have all this electricity going along from one star to another, and it has to be physical because they say this is gravity. This is what holds a galaxy together. This is what holds a star to another star or a planet to a star. All of this is done with electricity, the gravity, the so-called gravity. They say it's positive attracting negative, okay? How positive attracts negative, we have no idea. They just say it is so, right? And that's the problem with the electric universe in great measure, that they borrowed the language from the establishment. They're using the same language. And that's why they're never going to get through first to the establishment, then to any rational individual. No, of course not. You got a problem. You got a problem because you're using their language. You're using their atom. You're using the planetary model to explain electricity, and then telling me that a star creates electricity and that's what binds it to another star or to the galaxy or to whatever. If the electron is moving in one direction, they're all flowing out of one star and from another star to this star, how does that series of stones traveling one way, how does that produce attraction? Please explain. And the way they explain it, say, well, positive attraction, negative. Oh, okay, that explains that. I didn't know that. And that's one issue. The other issue is, don't all these electrons go through each other? I mean, with so many electrons flying from all these galaxies to every galaxy in the universe, the universe is filled with plasma, right? With all this vibrating electrons. Don't these electrons collide? Or do they go through each other? So again, all these people try to avoid the collision question because they're not treating their proposals as objects. They're not saying, I'm talking about objects when they're thinking about that. They're talking about this abstraction that they need in order for you to understand their theory. But I cannot understand it with abstractions. If you're going to put a heart and you're going to put, a brain, then talk about heart and brain. Don't switch that in the middle of your dissertation and say, well, I was really talking about love and mind. That's not the way it works. Not in physics. Okay? In physics, you need physical objects. And yeah, so there's no theory that anyone can come up to me and say objects don't go through objects, because they have to do it with so many electrons, so many atoms, so many plasma, so much ether, fields, energy, mass that we have in the universe. It's impossible for whatever mediates those transactions not to collide. They go through each other. And so every theory has objects going through objects, things going through things. There's not one that cannot have that, whether the proponent knows it or not. The issue here is that they're not aware that their theory implies that. It includes it in the theory. It's embodied in the theory that they're explaining. And they never were aware of it, because that's when they switch over to the abstraction and say, well, I was really, talking figuratively. You're not supposed to take my objects literally, etc., etc. That's the whole problem. That's why, every theory today on planet Earth and that has ever been has objects going through objects. So please do not ask me how a rope goes through another rope, because every theory has objects going through objects. Let's make sure we understand that. Okay, and this leads us into the issue of what is physics. Okay, and because we have all these people who, celebrity especially, and all they do all day long is talk about physical interpretation. They give you an explanation. They give you mechanisms, causes. That's what they talk about. They talk about them in their shows. They talk about them in their interviews. They talk about these in their documentaries. Everywhere, that's all they talk about. They talk about qualitative stuff. You never see an equation. You never see, they hardly ever do an experiment. Maybe someone might have done in the past. But in general, they don't do an experiment right there in front of you to prove something to you. And they don't go out there and bring math and equations and show you the equation. What they do is they say, this is how the universe works. And he begins talking about, the explanation, the mechanism, the causes, the way the mathematicians envision them, right? And so here you have these fellows. These are the famous gurus out there today. Okay, some of them are dead, like Feynman and Sagan, right? But these people, they talk about physical interpretation. That's all they talk about. You won't find anything other than physical interpretations when these people talk. So what's the problem? Well, the problem is that that's what they talk about. But when you put them against the wall and you begin pummeling them, against the ropes, they say, well, that's not what we do. What we do is equations. What you're talking about is philosophy. Go to the philosophers. They'll tell you what they interpret out of all this. So for the last hour, the guy talked about physical interpretations. When you tell him that what he said was ridiculous and irrational, that's when he says, well, by the way, we don't do that. That's not in our line of work. That's not in our job description. So why did we ask these people if it's not in their job description? Are they philosophers? Do they have a degree in philosophy of physics, philosophy of science? Do they have a degree in philosophy at all? What authority, we're going to talk about authority, what authority do these people have to talk about how the universe works if they're going to dismiss that at the end of the show and say, well, by the way, that's what they do in philosophy, not here in mathematical physics. So why are these mathematical physicists doing philosophy? Why are we asking them these questions? We're asking the wrong people these questions. We're asking, how is it that this falls downwards? And they say, oh, that's philosophy. This is a question of philosophy? Yeah. Oh, okay. Well, if you say so. Okay, and here we have one. His name is Sean Carroll. And listen to him. He's going to tell you a little bit about the difference between physics and philosophy, the way he sees it. Okay, listen to him.
There is a long-standing relationship between physics and philosophy. The two disciplines are a little bit different. They have absolutely different aims, but their subject matters often overlap. What philosophers try to do is to really understand the logical inner workings of something. Physicists, like myself, are often very happy just to get a theory that works. A theory that makes sense is a little bit too much to ask. And you might think this is not possible, but we have it all the time. Quantum mechanics is a great example of a theory that doesn't make sense to us, but it works, so for a physicist, that's fine. For a philosopher, they would like to do a little bit better.
Okay, so this is from the horse's mouth. I mean, they say quantum mechanics doesn't make sense, and Feynman already says we don't understand quantum mechanics. And these people say, look, we don't understand that, but we don't care about understanding. What we do is math. We do equations. So they spend all day long talking about, how the universe works, how quantum mechanics has been proven to work because otherwise computers wouldn't work, right? They've already proven everything. They've proven that general relativity is correct because otherwise GPS wouldn't work. Technology, right, proves the theory. And then they say, we don't understand it. And when you say, well, where do I get understanding? Oh, go to the other side of campus. Go to see the philosophers. They'll tell you how it works. And where do the philosophers get their cues? Well, they get them from the mathematical physicists. So we have this runaround, okay? Circular runaround. So one side of the campus sends you to the other side of campus. So, is physics about physical interpretations? Are physical interpretations a part of physics, yes or no? This is a black or white question. Otherwise, these people don't know what their subject matter is, because if everybody and their mother thinks that, this falling of an object downwards is part of physics, and this is a question that a physicist has to answer because it's in their job description, and these people later on tell you that it's not, then we're asking the wrong people. And then the question also pops in, why did they attempt to answer the question in the first place? I mean, if it's not in their line of work, why are they answering questions that are not part of their job descriptions? Very simple. So we have a problem. These people don't understand or don't know, right, what their subject matter is. They don't know what physics is about, okay? And went it down, asked Nobel Prize. Here's good old Max Born. He says, since the development of special relativity, theories using a substantial ether fell out of use in modern physics and were replaced by more, abstract models. And abstract is the opposite of physical. So if physics is about the physical, abstract is about abstractions, right? So these people are not physicists, they're abstractists. And I'm now convinced that theoretical physics is actually philosophy. So that's what's happened here. They originally tried to answer the question, and because they couldn't, they finally said, like Richard Feynman says, they finally given up on that. They don't do physical interpretation. It used to be part of physics, but somewhere maybe in 1950s, 60s, they finally gave up and said, look, we don't understand it. We'll never understand it. Maybe someday we'll understand it. But right now, we're going to say that physical interpretations, qualitative interpretations, are not a part of physics. So who should you ask out there? Biologists, archaeologists, maybe, I don't know, a doctor, a medical doctor, who should you ask about these questions if not a physicist? What do physicists do? Just a bunch of math? And then they say, let me interpret that for you, and gives you an irrational explanation and tells you he doesn't understand it either, and go ask the philosopher? Oh, great. And then, of course, you have the other side of the story, and here, very briefly, you have another fellow, his name is James Beecham, and that's what he has to say.
What causes gravity? So physics, as you know, this is the type of question, what causes gravity? This is the type of question that keeps physicists up at night. Because physics is, among other things, as you know, the search for mechanisms, the reasons or explanations for why certain things happen the way they do.
Okay, so is it or ain't it? I mean, do physicists, are they supposed to answer these questions or not? James Beecham says, yeah, that's part of their job description. And you have the others that say, no, it ain't. And so we don't know. The jury's still out. Someday they'll tell us whether physics, right, answers these types of questions. Meanwhile, you're going to have to do it on your own because they have no answers. Okay, so I have to define this, and here it is. Science, rational explanations. What is physics? One of the two branches of science. Physics is the rational explanations of causes and mechanisms. That's what physics is, and only that. We use no math. We don't do any observations, predictions, no experiments. In science, what we do is explanation. You can do all the experiments you want in your own, dark basement. Do all the experiments you want, no problem. That's not part of science. Science is when you come to the conference and explain what you understood, and you explain the mechanism that you got out of that. But as long as you're in your basement and you do an experiment, don't show it to anybody, hopefully that's not science. Science is when you communicate your theory to someone, to a group of people, and say, look, this is what I propose. Then we have science. Then science vibrates. But as long as you stay in your dark basement and do experiments, or do them in front of people and say, look at the experiment, like Faraday used to do. He used to do experiments, didn't understand a single one of them, but he used to do experiments. Great. So was he a scientist? Obviously not. He could not explain his mother. Okay. So, yeah. And what is the explanation? Causes underlying a phenomena. And that's where you have to break your brain, when you have to come up with causes. Okay. And for that, there's only one way, and that is to identify the invisible, intangible mediators that Mother Nature and Father Universe use. Then, only and then, can you explain, phenomena that are mediated by invisible, intangible mediators. Only then. Okay, so we have the foundations here. I talked about this the other day. Foundations of physics. I had to come up with them. What are the foundations of physics? Well, we start with this, which is I call the golden principle, that you must have an object. Physics requires an object. You can't do physics without an object. If you do physics without an object, like, entanglement or action at a distance or remote control, that's known as witchcraft. It's known as, black magic, voodoo physics. That's what it's known as. Okay, so no, we don't. We always have objects mediating transactions. Otherwise, you're doing black magic. And that's what all these people do. They do it even worse. They're introducing concepts in lieu of objects. Okay, so we had to create this tool known as the universal movie. And what we have in a single frame are static concepts. In other words, such as object, distance, location, and existence. In other words, all you will see in a single frame is every atom in the universe at a given distance from all others, distance being separation, not distance traveled. And they all have location, meaning the set of distances from one object to all others, one atom to all others in the universe. And existence, we defined as an object that has location. And all the dynamic concepts which are at the bottom require at least two frames of the movie. And there you see several of them. Those are just examples. Okay? But you can see plasma, ether, field, energy, and time are all at the bottom. They're all dynamic concepts. They are not physical objects. Physical objects, that which has shape. Okay, so this tool is useful. Why? Because in science, right? Why? Because it allows you to freeze the universe. and find out what's there before you move anything. Okay? It's important to stop the universe, freeze it, every atom where it's at. Okay? Magic wand from God, you say, abracadabra, everything stops, nothing moves. Like one case of, I think it was the, not the Outer Limits, the other one, the Twilight Zone. Twilight Zone, the guy freezes the whole universe, except him, right? He could move around, okay? But you need to freeze the universe. That way you can identify what's there before you move anything. Okay? Only then can you start making progress. You got to identify first the object, especially the invisible, intangible objects that are hiding in there that Mother Nature and Father Universe have hid from our eyes and our hands. Okay, so here we have it. This is what an object is. Okay, foundation of physics. We have the golden principle, which is physics requires an object. What is an object? That which has shape. If it has shape, it's an object, qualifies as an object. And of course, if we have that which has shape, we have to get the opposite, which is that which doesn't have shape, and that's what we call space or nothing, okay? Or zip, vacuum, whatever you want to call it. Doesn't matter. Nothing is that which doesn't have shape, okay? So one is that which has shape, and it's an antonym of the other, which is that which doesn't have shape. Okay, and here we have a fella who has a different definition. These are some of the definitions mathematicians come up with. This fellow is a mathematician also, and he says the following. Wrote a book, Motion Mountain, okay? You can find it on the internet. Objects are described completely, right, by their mass and their electric charge. So in this fellow's mind, and surely in, I'd say 99% of the mathematicians out there, they don't think of an object as a thing that has shape. In fact, he doesn't even mention this property. He says, mass and electric charge are the only intrinsic properties of everyday objects. He doesn't mention the only one that is really correct, which is shape. All objects have shape. Whether they have mass or electric charge, I don't know, but for sure they all have shape. And he doesn't even mention that because they're interested in the mathematical aspect of how they're going to use this object, in their equations. And they can't put the word shape in there. They can't put a form there either. What they have to do is put a number. And for that, they had to talk about charge and, mass, things of that nature, concepts of that nature. And it's interesting, he talks about the same error people make, that they talk about the word state. They use the word state, right, which is a static concept. State is static, okay, of objects. And when he talks about varying aspects, and what does he mention? Momentum and angular momentum. Now, momentum is a verb, okay? It's not a static, it's not a state of anything. Okay? No state called momentum. Okay, so some of the concepts that we went through this past week or these last couple of weeks. One is distance. Okay, here it is, foundations of physics. After space, we have distance, which is related to space, obviously. It's a separation between two objects. And that's different than distance traveled, which is what mathematicians used. And why do they use it? Well, because the mathematician is only interested in unrolling the tip of his measuring tape. So whether he measures a table or the space between two tables, the vacuum, out there in space, like two tables, right? If you're measuring between two tables, then they have to unroll the measuring tape for the table or for the space between them. Okay, and so, I like to say that distance, right, the real distance, the one of physics, is what lies between two objects, between two lengths. Okay, that's the correct way of looking at this. Distance is not distance traveled. Distance is separation in physics, not in math. Okay? Math is something else. We're talking about distance traveled. And we have location. What is location? Well, location is the set of distances, one atom to all others in the universe, or from one object to all other objects in the universe. You can select the system that you want. You can, branch it, bracket it wherever you want. Okay, so yeah, location is the set of distances. You want to have location? You want God to have location? No problem. God has to have distance with respect to every object in the universe. Then you say that's the physical location of God within the universe. Okay? And if you say, well, God's outside, my God is outside the universe. Well, is there a straight line of direction from me to him? I mean, can my nose have a straight line of direction with his nose, right? Or my chest to his chest? Can he escape my radial, pointing? If he can, well, he's more than magical. Okay, so here we have existence. God wants to exist, he has to have presence. So aside from being an object, having shape, physical, that's what physical means, object, thing, it has to have presence, has to have location. Okay, so he's got to have both. It's not enough for God to be an object. God has to have location in addition to. Okay, what is motion? Well, two or more locations of an object. There we have it. Object is at two locations, one object, right? Then we can say it moved. That's what we call motion, movement. Okay, two locations or more, right? And you can chop that up as much as you want. Whenever you chop motion or time into as many pieces as you want, you cut it in half, cut it in half, cut it in half, cut it in half, you will always end up with two frames in the universal movie. You end up with two frames. Why? Because motion is defined as two locations, and that requires two frames in the universal movie. Same for time. Okay, so you can chop up motion, like Aristotle tried to do. He chopped up motion, says, well, where do we end up? We have all these locations in between, all these points in between 2 points, right? Because the points and the line were really, points were locations and lines were itineraries, trajectories, right? Motion, movement. And so he said, you can chop that up as much as you want. Yeah, you can chop it up as much as you want. No matter how far you chop it up, you will always end up with two frames in a universal movie. And there you can see how powerful the universal movie tool is to address these issues. Okay? Because now you can explain that both motion and time, no matter how much you chop them up with, you will end up with two frames of the universal movie. You can't do it in one. And hopefully the particle did not create a clone of itself in the next frame, because then in every frame you're creating all these clones, right? Means you can travel back in time and land in that atom, right? In the past. That means all these atoms are there. Then there is no motion. All you have is cloning of every atom in the universe. And I don't think God has time for all that. I really don't. I think he runs a much leaner universe, okay? Okay, so here we have finally concept. What is a concept? Well, we come up with this. There's two types of concepts, by the way. We have the static concepts in the universal movie and also the dynamic concepts. What is a concept? A word that invokes or embodies two objects, okay? And give me a second here. We have concept, and what do we have? We have two words or two objects or two words that are treated as objects. And so we have a relation between them performed by someone, okay? And so a concept is, you need the word concept in order to define, you need to define the word object before you can define the word concept, okay? Because as you can see, you require the word object. You need two of those in order to define concept. So you cannot define the word concept before the word object. All these words have to be defined in a certain order because one is dependent on the previous one. Okay, so you need to have these in the right order. And so yeah, with the concept here, let me show you the universal movie again. Here we have it. Okay, and you have the ones at the top are static concepts. Okay, and the ones at the bottom are dynamic concepts. Okay, what do we mean by that? Well, the ones at the bottom embody motion, okay? And the ones at the top, they don't embody any motion. And that has to do with the definition of these words. And a lot of people have problems understanding that. You know, that how can that possibly be that you have a static concept? For example, you have direction, right? Direction is a static concept. You don't need to have any motion for direction. You can have an A and B, a beginning and end. You have a line, right? And you say that's the direction, right? And don't you need to have an observer, establish a relation between beginning and end, A and B or whatever? Yes, all concepts require two objects, and you have to have an interpretation by the person, who's talking about that concept. So all concepts have an observer by definition. Okay? But what are we saying? We're saying that the definition of the word in question, the word direction, has no motion in it. The word distance, separation, has no motion embodied in the definition of the word. So we should not confuse that with the fact that you need an observer to establish a relation. Relation, obviously, is a dynamic concept. It's the word relation. But what we're saying here is you got to look at the definition of the word direction, the word object, the word exist. None of them carry or embody any motion per se. Okay? And for that, you need to go to the definition of these words.